All right, so we are talking about geometric sequences, which we know from class is patterns of numbers that increase according to multiplication, either multiplication by a whole number or by a fraction. And so today I'm not going to be in class, so I wanted to show you how to complete the example problem from your worksheet that we started yesterday. I'm sorry about the blue marker on my fingers. So you have all of this on your worksheet, and then your work in class is going to be to work on numbers 1 through 8 here. But just because it's easier to see someone do it out, everything that I do in this video is going to be related to this problem. Okay, so that being said, here is the geometric sequence that is used in this example problem. And we can tell that it's geometric because of the patterning of the numbers. The fact that to get from 5 to 15, we multiply by 3. And to get from 15 to 45, we also multiply by 3. And we can assume that this pattern will continue, and we'll be able to multiply by 3 however many times to get the succeeding numbers. So what this means is, as a recursive formula, so that's the one that we would have to use redundantly to get one term each as we go along, we would have each term in this sequence, so any term in this sequence, a sub n, would be equal to the element before it, so that would be a sub n minus 1 times the common ratio. And of course we talked about the fact if for some reason it's not as simple as just, 5 times 3 is 15, we can always say, what's a2 divided by a1? What's 15 divided by 5? That's 3. And we can figure it out that way. So that's a recursive definition. Each value is the previous value times r, the common ratio. But that's not especially helpful, because in order to get something like the 100th term, we would need to know the 99th term. And so that's not really the kind of formula we want. It's true, but it's not especially useful. So we want to talk about an explicit formula for geometric sequences. So here it is, or we'll start it, I should say, the explicit formula. So that means we want to find any term in the sequence based on just simple information, like what is the first term and what is the common ratio. So let's think about how we get each of these values. We'll call this a sub 1, a sub 2, a sub 3. We could continue a sub 4, or we could go on and on and on until we got to a sub n, any term in the sequence. In order to get from the first term to the second, we'd say, let's take the first one and multiply by 3 once. So a sub 2 is 5 times 1, 3. In order to get to a sub 3, we'd have to take 5 and multiply it by 3 2 times. So the third term is 5 times 3 times 3. To get to the fourth term, it would be 5 times 1, 2, 3 threes, right? So the fourth term is 3 ratios. The third term is 2 ratios. The second term is 1 ratio. So we can see this pattern where if we wanted to find the nth term, all we would need to do is take the first and multiply it by n minus 1 common ratios. So here's a sub 1. We need to do n minus 1 common ratio. So here's how that works. Hold on one second, Daniel.
There's a color in here, and I can't get it out because it's stuck.
How about I help you in just 1 second, because I'm almost done. All right. So we have any term in the sequence should be the first term times...
I can hold it out there.
Oh, thank you. Let's leave it here for right now. It would be the first term times the ratio n minus 1 times. Because remember, an exponent just means that we have a factor that many times. Let me show you with real numbers. Let's use 5, 15, 45. Let's use that pattern with a common ratio of 4 to figure out let me get a different color here, what the 12th term of this sequence should be. Now we're using this explicit formula as our pattern. So to find the 12th term, the first thing we need to know is, what's the first term? Well, we know that's the number 5. So it's the first term, 5, times the common ratio. Well, we know the common ratio is 3. So it's 5 times 3, but how many 3s? Well, we want to find the 12th term, so we need 11 3s, 11 common ratios, n minus 1. So since n is 12, n minus 1 would be 11. So 3 to the 11th power, if you were to put that into your calculator, you would get 177,147, which is just such a fantastic number, times 5, because remember order of operations. This comes first, that's second. Oops, I'm out of the picture here, sorry. So 3 to the 11th is this awesome number, times 5 because of order of operations. And if we multiply that out, we should get our 12th number, which is 885,735. So the 12th term of this sequence would be this value here. And again, we got that by using our explicit formula. And that should do it. Hopefully you caught all of that. Let's see if I can zoom out here so you can see what's going on. There we go. And you can use this video, or you can use the example on your worksheet to go back to as you work through the example problems.